Hi everyone, my name is Keming. I'm a NASA Second Fellow at MIT. So in today's talk, I'll be talking about a FFP survey program that I've been leading, tentatively called Rogue Planet Host Search. So first of all, I'd like to thank the organizers for scheduling me to the third talk of the session, which means I get to jump straight to the content, skip all the introductory stuff. And as we have learned from Taka's talk, microlensing free-floating planet candidates possibly outnumber stars and bound planets in our galaxy, possibly by an order of magnitude, with the caveat that they could be either unbound or on very wide orbits. So the crucial question to ask is, are these microlensing free-floating planet candidates truly unbound, or are most of them actually just wide orbit planets? And Sean's talk just gave us a great demonstration of how a high angular resolution imaging can be used to help to resolve this ambiguity by trying to directly detect the FFP host. But for individual events, it's quite challenging because there's always some possible FFP hosts that would evade detection simply because they're either too far away or too faint. So to answer this question really needs an investigation of a large statistical sample. So this brings me to our Rogue Planet Host Search survey, which aims to characterize most microlensing FFP candidates detected to date, with the goal to establish a relative fraction of FFP's candidates that are truly unbound versus wide orbit. So last time I counted, there is approximately around 30 microlensing FFP candidates detected to date. And good news is that we have already observed half of them already, 15 of them, between 2024 and 2025. So in the first year, we observed six FFP candidates. Surprisingly, 5 of them, so nearly all of them have host candidates. And it partly has to do with how long ago these events occurred. So the search region is pretty large, and the chance of a random field star just lying in that region is pretty high. So it requires a second epoch to measure proper motion in order to predict the location of these host candidates back during the event. And last year's meeting, I remember Sean talked about his analysis of 2 of those events with the host candidates. So in 2025, we took the second epoch, so basically no host candidate project close enough to the source star during the event to be confirmed as a host candidate. So these are still most likely to be unbound, and we observed 9 more. And so apparently some of these would require a second epoch for themselves too. And the good news is that we already received additional 5 half-nights on Keck in this summer next year to continue to expand our sample. So for this project, we're using the laser guide star adaptive optic system on the Keck observatories. It uses this LGS AO system to remove the blurring effect of the atmosphere. So basically, effectively putting the telescope in space, making it diffraction limited. So the angular resolution is comparable, if not better, than HST. But what's better is that the aperture is 5 times larger. So in a very short amount of time, we can detect possible M-dwarf hosts out to the bulge distances with a reasonable amount of exposure time. So it becomes feasible to investigate a larger number of these candidates. And it's useful to demonstrate this technique for a tangentially related science, which is trying to find white dwarf hosts for microlensing planets. So 2 such planets have been detected to date, one of which is led by myself on the right side. And the system has a striking similarity to solar system's eventual fate, but I don't think we have time to talk about that today. But it's worth noting that post-AGB evolution is one of the mechanisms that produces free-floating planets. So it's a good opportunity to review the basics of how these follow-up investigations work. So at the time of the event, so in terms of a bound planet, at the time of the event, the lens and the source nearly align perfectly. And the Likert model usually tells you how the relative power of motion, so you can predict after certain years where the host star would be. And that will be on the left case, that will be the contours predicting after certain years where the host would be. And in that case, the planet host is known to be around half solar mass at around 2 kiloparsec. So it is expected to be bright, and they do not detect it. So they concluded that the host must be dark, so it's a white dwarf. So there's one key difference in our investigation is that for FFP events, it is the planet, it is the FFP that aligns nearly perfectly with the source star. The location of the putative host depends on its projected separation from the planet. And as you can imagine, if the FFP is actually a bound planet on a 1,000 AO orbit, it'll have a pretty large offset from this contour of tens or hundreds of milliarc seconds. So one point to note is that the FFP host is not expected to project exactly back to the source during the event. We are seeing exactly a case like this, which is the terrestrial FFP candidate that Taka just talked about. There is no signature of a host star in the light curve, which rules out hosts to approximately within 5 to 10 AU. And the mass is around 1 Earth mass. So the left stem shows a zoom into the event location of our 2024 data. On first side, you see, so the bright star at the center is the source star. And at first sight, there's another star that's pretty close by. So what exactly is it? And because of how large imaging data set we're dealing with, dozens of events, I've recently developed a semi-automated PSF modeling pipeline that utilizes some of the advanced algorithms from high contrast imaging, which turned out to work pretty great. So second panel shows a PSF model built by the algorithm. Third panel shows the source star modeled as a single star. You see this obvious dipole pattern suggesting that it's composed of two stars that are very close to each other. And this is consistent with Sean's analysis presented last year. After fitting the central star with two stars, the residual is pretty clean. And you see the scene is composed of 6 stars. So I would say star number 1 is the source star. I don't have the time to discuss how I reached that conclusion. But the thing to note is that, so for this event, Likert model predicts that in 2024, the FFP should be around 100 milliarc second away from the source star. And none of the stars in the scene is at this expected separation. But as we just talked about, that is entirely fine. It's not saying that, it's not a reason to reject these as host candidates. And what we need is a second epoch. What's relevant is their locations during the event in 2008, which is 16 years ago. So a second epoch was taken this recent summer, and central 2 stars have common proper motion. So one of them is the binary companion to the source star. Not very surprising. And what's really interesting is the left 2 stars. It turns out that both they actually have a similar proper motion relative to the source star, at around 6 milliarc second per year, pointing towards, approximately towards the source star. So first of all, this matches the Likert model prediction. But a weird aspect of this is that this would imply that these two host candidates would be at a further distance back in 2008. Precisely 300 milliarcsecond. If we assume a typical lens distance of, let's say, 3 kiloparsec, that will imply a planet-host separation of 1,000 AU. So these two stars also have hints of common product motion to themselves. So they might be part of a binary system too, but the error bars are not, measurement is not precise enough to make that statement. But anyways, how do we know if they're the host? How do we know if this planet is actually a bound planet at 1,000 AU or not? So you might try to think that because the measured product motion matches the Likert prediction, then that gives some level of credibility to this hypothesis. But it doesn't help to know that, it helps to know that the most typical relative product motion along this line of sight is also 6 milliardsecond per year with a slightly broader distribution. So a lot of field stars would end up consistent with the Likert model prediction. It's a really unlucky coincidence that the Likert predicts a pretty typical product motion along this inside of this field. So most of the evidence actually come from the fact that the host candidate, especially the brighter one, is projected extremely close to the source star. And this field is actually not particularly crowded. It's pretty sparse. And within a certain area centered on the source star, there's an average of 0.2 stars, field stars, as bright as the host candidate within a square arcsecond region. That's basically the red box. And there is only a 3% chance of observing a random field star as bright as the host candidate, lying as close as the host candidate. But perhaps what's more relevant is the host location in 2008. And because it's further away, there's a larger chance of having a random field star projected as close as the host. And that probability reduces to approximately 6%. So it's basically a 1 to 2 sigma evidence based on the proximity that this bright star is a host to the FFP. It's not really, it's pretty marginal evidence. And I think it's made even more marginal if you compare to what an extraordinary claim that we're making, that a planet is at a 1,000 AU orbit. So simulations have shown that it's very difficult to place a planet at 1,000 AU. And I think that we'll hear Sean Raymond talk more on that later today. But one of the possible mechanisms is that a planet is scattered on an eccentric orbit and then is stabilized by a closer flyby so that it's shielded from additional perturbations in the interplanetary system. So it remains stable at 1,000 AU orbit. But as far as I'm understanding their analysis in their simulations, basically for 10 ejected planets, there's less than 1 planet stabilized to these extremely wide orbits. So what's that saying is that we're dealing with 2 hypotheses. One, the star is a host. The other is a random field star. And they're basically equally surprising. It's equally surprising to find for FFP candidate to be on a very wide orbit. And the level of surprises is both on the order of a few percent. So if you do a Bayesian analysis, current evidence would not strongly favor either of these hypotheses. So the conclusion is that this 15919 FFP candidate could be a very wide orbit bound planet. but there's insufficient evidence to claim such a discovery. And it's unlikely that future observations could significantly increase the evidence. I think unless technology advances and we can send a spacecraft to the system and see if they're bounded. Anyways, so yeah, this does highlight the limits of microlensing to probe this population of very wide orbit planets, basically because of this crowding from crowded fields, and especially Roman will be observing even more crowded fields. So that'll make it even more challenging to definitively confirm planets on these wide orbits. As for the other candidates, we haven't confirmed, based on the two apart motion measurement, any planet with a FFP host projected within around 100 AU orbit. So it's saying that it's very likely at least some FFPs are truly unbound. And our next observation is coming up in half a year. So we'll be able to establish the relative fractions of a bound planet versus truly unbound planet versus wide orbit planets fairly soon. So with that, I'll be happy to take questions.
So I'll just use my prerogative here to point out that if we do get parallax measurements, then that at least gives you a direction up to the twofold degeneracy.
Yeah.
And so that would help a little bit, right?
So to continue from Scott's comment, yes, parallax would help. And there's also some special situations that'll allow you to claim a stronger evidence. For example, very, very slow relative probe motion or very, very fast relative probe motion. Because the precision in relative probe motion in microlensing is limited by the precision in the source angular size, which is around 5%. So you can't get a probe motion measurement, probe motion prediction better than 5%. But if your probe motion is extremely small or extremely large, then the fraction of field star matching that prediction would diminish. So there would be some, I would say there would be some situations that might enable such discoveries.
So Sean has the mic, so we'll let him go, and then we'll, I think, go over there.
A great talk, Keming. I recall coming to the same conclusion about the source having a companion from that the dipole feature in both years. So that two quick questions that would come from that. Do you think there's any merit in remodeling the event with a binary source, the microlensing event with a binary source, and also perhaps looking in the many year baseline after the 2008 lensing event for any interesting thing in the photometry?
So I think based on the binary separation of 18 milliarsecond, then it's like, I don't know, maybe thousands of angular Einstein radius away from the FFP. So it will probably not cause a light curve signal. And as for future observations, it's one interesting aspect is that the host candidate is still moving towards the source star. And I think probably it'll project closer to the other the source binary, but I don't think there's not precise enough data to predict where it'll project closest to that star, but maybe it'll produce a signal in a couple of decades.
Might have a better chance of doing an astrometric signal. And there's a question over there.
I am Matthew Penny, Louisiana State University. One possibility you didn't mention for maybe helping this is if you had colors of companions, which they're resolved. So this is easily possible. If you take the data, you could actually demodel it and get a distance, and that would narrow down your possible states of like you've got a angular Einstein ring radius estimate as well. So it's, it would possibly improve the constraints you can.
That's an excellent point. So if you have a parallax measurement from Roman, you know where the FFP is. And if you have a distance measurement for the host from color, that'll be the excellent alternative source of evidence.